one more type of a heat exchanger that we have not talked here, let's take a little look at it, then we leave it, is what is called a boiler. Very common device. That's your main thing that produces high pressure, high temperature steam for generating electricity. A boiler, I can even put it this as a nuclear reactor, or in these days even solar collectors. What happens here is that on the tube side, it is the same process that happens in the heat exchangers that we have seen. So you have tubes in which the fluid, cold fluid enters, it gets heated up and comes out. But what's happening outside the tubes is that in the case of a boiler, we are burning a fuel. So there's a tube there, into which we are putting the cold fluid, but outside here there is a flame or a fire or a combustion taking place, and this is transferring heat to the tube. This is not just by convection like we saw earlier, but both convection and radiation, it is heating it up. In the nuclear reactor, the heating takes place because you have a fuel rod in which heat is being generated, and outside this, the coolant is going out, and this coolant gets hot and comes out. This could also result in phase change if it is a boiling water reactor, a BW water. And a solar collector, you could have a bunch of tubes in which this fluid is flowing, and they are just getting heated from the outside by solar radiation. So the outside is not strictly a heat transfer in the classical sense that we have seen, but at least on the tube side, our analysis will be exactly the same on what we have talked a few minutes back. So there's only a tube side fluid, and its analysis can be done the way we have looked at it. Okay, the next set of equipment that are used, I put three names here: a compressor, a fan, or a blower. There's slight difference between them, but what all of them do is they cause a gas, typically air, to flow. And in particular, we are looking at the fact that these are what are called centrifugal machines, as different from positive displacement devices. So this would, the simplest example of a fan is your ceiling fan. So all you have is a hub with blades on it, and there's a motor inside this, so you give electricity to it, and it causes an airflow over there. So the same thing with more blades, like say exhaust fan of the kitchen or the bathroom, that would be a fan. A blower is slightly different. You would have seen a blower in some of the desert coolers, where there's a circular device into which air goes in, and on this there's a wheel with these type of things. This is rotated, and as the air comes in from this side, it throws it out on one side. That's one type of a blower. So what fans and blowers do is that the pressure increase in these devices is very, very small and very modest. It's not very large. Millimeters of water, tens of millimeters of water is all you get here. And we don't really need much more than that. So say a blower that is used in the air conditioning of a whole building will be one blower at one point, which is called the air handling unit, AHU. That takes in air, part of the air from the room itself, gets in some fresh air and blows it, and that goes over the evaporator coils, and that you get cool air inside the building. That's the AHU. Compressors, the difference is that delta P here is quite large and substantial. So here there is compression taking place, so density increases. Here density is almost constant. So we can treat this as incompressible flows. So we can treat that air density is not changing, even though it is air, and small changes in pressure are there. But here we cannot make that assumption. And the reason we say that density is constant is because delta P is very small. That's why we can say the constant density or incompressible flows, this would be treated as a compressible flow with pressure change. In making schematic diagrams, we use three symbols over there. So this means that the gas or air goes in. Inside this, there is a shaft on which there are blades. The air keeps flowing over this, or the gas keeps flowing over this. There is a rotatory part which will give momentum to the gas, and a stationary part which will reduce the kinetic energy and increase the pressure without any work input or heat input. Then the next stage will do it a little more. So like that we do the compression. First we give momentum, so of the energy, and then we retard it. When you retard it, it's like a diffuser basically what we have, and because of this the pressure goes up. And then we can again put it into the next set of blades, do the same thing, and do the same thing here, then again. So this would be called multi-stage compressors, and all practical compressors by and large are multi-stage. The aircraft engine is a good example of that. In schematics, we can also use this symbol, largely for, sometimes for compressors, but largely for fans and blowers, these symbols. Okay, so now we said, how do I analyze these? And for that we accept that to do this happen, there has to be a work input in this. So we can show here by a symbol and write a motor, that is a motor powering this, or this has got a motor, this is powering this device. So what it does is you have work input taking place, and the system we first define in all of these. We say that look, I will take all this is my system, or one can say that this is the system excluding all the metal and only say the gas or the working substance which is there, air or whatever. So this system has one inflow, one outflow, and there is a power, shaft power being input to this. So once we have drawn the system boundary, we know that these are open systems. Even in this case, the story is the same. We can show the system boundary to be like that. These are open systems. That means we know that conservation of mass, conservation of energy, and entropy equations, which ones to put. And then we say that this could be air, or it could be some other gas that may be there. Say methane, say natural gas, Mg. And then we say, okay, if this was the working substance, now what are the equations we have to write? So that we do that. And the next step is what the assumptions. And that helps us to get that big equation into a simple thing. And the main assumptions we do here is firstly, of course, that being a flow system, we say this is steady state. Nothing changes with time. Then we say that delta PE is equal to 0 because the potential, the elevation difference between these devices, in some cases it is negligible, in some cases it may be a meter or two, and meter or two rho GH is negligible compared to the other changes that take place here. So delta PE equal to 0 is justified. Unless otherwise given, delta change in kinetic energy can be assumed to be 0 if there is no mention about velocity in the problem. However, if the velocity typically either at the inlet or at the outlet or in both places is specified, then this is not to be assumed. Then the velocity term will remain in the first law equation. Okay, so if V1 or V2 or both, they are given, then this is not the case. Okay, so then this will be wrong. So once we do that, we get to the equations, and then we are in a position to solve. Now, this type of device, and this is where engineering comes in, they always handle a single phase flow. Even the earlier device, which are the positive displacement devices that I mentioned, they also are designed for handling single phase flow. The practical engineering of these machines, if you had a wet substance going into this, is extremely difficult, in large part because liquid will accumulate here or there by gravity, or liquid droplets will go and hit the moving parts and break it up. And so we always make it a point that no matter what type of a work transfer device it may be, whether it is a positive displacement, compressor, fan, blower, these always handle single fluid. So these devices or that other earlier device, I said they will be either handling a vapor or a gas. I am not putting the word liquid over here because that we will see in a minute. That machine that handles liquid is not called compressor, fan or blower, but it is called a pump. So we'll look at pumps separately. Okay, so this is very, very important. The moment we say it is vapor or a gas, if it is a vapor state, it will be superheated vapor. It cannot be a wet state. And it could be possible to assume ideal gas behavior, but if it is like nitrogen or oxygen, in that case, ideal gas behavior is okay. Otherwise, like in a refrigeration system, we will have to go to the property tables and get the data from there. Nevertheless, this process can be approximated by something like PV to the power n equal to constant. If it is PV to the power k equal to constant, we also know additionally that this is a reversible isentropic process and I can use this equation in one. But the important part is that compressors, fans and blowers, they handle a gas or a vapor and they never handle either a liquid, and of course no machine will handle a wet substance. And we'll see that in a minute on what it means for the implication in designing cycles. But the wet state inside a work producing device or a work consuming device is a big, big problem. So all engineers will do everything to avoid that. Okay, so that's the assumptions, these are the equations. Then we get the conservation equations that m dot 1 equal to m dot 2. We put the states 1 and 2 or inlet and outlet, and then get what will be the work transfer W dot CV in this case in terms of properties. On the property diagrams, say we take the TS diagram. If it is a vapor, we will have to show the dome, and compression will be from say this state to this state. This is what happens in a air conditioner or in a refrigerator. So we are well below the critical point. We are not very far away from the dome, so we will show the dome that this is the compression process. On the pH diagram, again we will show the dome, and we say, well, what are the constant entropy lines? Here we have assumed it to be isentropic. These are constant entropy lines. I say, well, what is the constant entropy line? This is the constant entropy line. Where are my states? We say, okay, your inlet state is there, your outlet state is there. This is the compression process. And now we say, well, what if the process is not isentropic? Okay. But being small devices and we do not want to make life too complicated, we not only say that this is the case, we also say these are all adiabatic. So the important things about work consuming, work producing devices is firstly they are adiabatic, and from an engineering context, we necessarily have a single phase in it. Now if it was not a reversible process and we say it goes to the same final pressure, so in this case the constant pressure lines are here and here. So the inlet pressure is assumed to be constant, the discharge pressure is also the same, so this was P1, this was P2, and then the anisentropic compressor would do that. So this we will denote as 1 to 2, S means isentropic, and 1 to 2, this is the real case. A dotted line because the process is irreversible. So if you have to calculate the real work from the isentropic efficiency, or if you have to calculate isentropic efficiency, we need to know one of these things, either this change, P change, or the work input. And two of these are known, the third one can be calculated. On the pH diagram, The discharge pressure is going to be the same, inlet pressure is the same, but entropy has to increase. So these are the lines of increasing entropy. So this will go off on that side. So if nothing is said, we say that isentropic efficiency is equal to 1. If it is the value is given, then we know that we need to calculate one of these 2 points from the isentropic efficiency. So those are the important things about fans, compressors and blowers, that we take that these are adiabatic. They will handle a single phase substance. This is not that thermodynamics says you cannot handle it. Thermodynamics says yes, you can put a wet thing through it. No, the science is not wrong. The engineering says that look, it's too much of a nuisance. Equipment becomes unreliable. We will not make equipment, and nobody makes equipment like that. And unless specified, we assume isentropic efficiency to be 1. If it is not 1, we have to take that into the problem and then begin to solve. So now we come to the counterpart of the compressors and fans, and we say, well, we now look at a centrifugal pump. The word pump means that this handles a liquid. But what we know from thermodynamics is that what we call in common language as liquid is, we can call it either a subcooled liquid or a compressed liquid. And in all cases, we assume that this is the symbol for that, a circle with an arrow. And we say that this is the inlet and this is the outlet. Inlet state is 1, outlet state is 2. Throughout the state, the process, it remains a liquid. We do not want a situation whether either the inlet is wet and then you make it into a compressed liquid. That's not something we can do. But like I said, the earlier principle about engineering is that this will be single phase. But there is one condition where we do have a problem. It's a practical problem whose roots lie in thermodynamics. We will see that in a few minutes. So what does a centrifugal pump do? Firstly, it's a liquid thing. The moment we say this is so let's go the systematic way that we would like to approach this. Having made the symbol, we say that this is our system boundary. And so, well, there is one inflow, one outflow, and to run the pump, we have an external prime mover. This could be a motor or a diesel engine, like you see in agricultural applications. So there is work input to the pump. We have one inflow and one outflow, and we say that our system is everything inside this, but that's only the working substance there. No metal, oil, anything else is considered. This system we know is an open system, so there is one inflow, one outflow. And we know that this is a liquid, so let's say, well, how can we then begin the analysis? First thing we assume is steady state. So when I'm writing this, we actually should be saying that this is assumed that there is steady state, and elevation references are very small. Delta Ke equal to 0 is okay. And pumps, even though they increase the pressure, they don't increase the velocity very significantly at all. So it is perfectly fine to say that, the kinetic earlier case elevation was 0, so delta Pe is equal to 0. Since velocity changes in the machine are very small, we can say the kinetic energy change from inlet to outlet of a pump is also 0. So with that, we know now that it's open system. What are the conservation equations we have to write? Then under these assumptions, what do the equations become? And in this case, conservation of mass becomes m dot 1 equal to m dot 2. And then we also say that this device does not lose heat if it is a hot substance in ambient, or it is not being heated. So we'll say that this is an adiabatic device. We said the same thing about the reciprocating machines. We said the same thing about compressors and blowers. Here also we say adiabatic means that Q dot Cv is equal to 0. So all we get is m dot 1 h1 is somehow related to m dot 2 h2 and plus q dot Cv. So you can write that equation. So although we had a very long equation to begin with, under these assumptions, the equations become very simple. And after some practice, you can directly jump to this if you are certain that all the assumptions are there and you are aware what the assumptions are, and you must write what those assumptions really are. So that's what happens. That's the equation, and then we can, sorry, not w dot c, this is w dot c, the work. So we can calculate the work. The difference between the treatment of pumps and the earlier type of machine is that here we have a liquid. We have argued from property considerations earlier that for a liquid, V is like constant. We say that liquid and solid are incompressible. That's the thing that we are saying, that V is constant. In which case, we know that H1 minus H2 is V P1 minus V. We assume V to be constant, and the question is which V to take. Should V be at state 1 or V at state 2? Either value would be okay because the difference between the two is very, very small. But if someone wants to be very, very clear and very precise, you can say that I will take V as the average of V1 and V2. But that really is not going to change the result very significantly because the change is hardly 0.01%, that type of a difference. So you can take either V1 or V2, but explicitly mentioned there in the solution that since the liquid is incompressible, we are taking specific volume of the liquid to be specific volume at state 2, whatever the pressure and temperature may be, or at state 1, if you know the pressure and temperature over there. So this is the thing we are bringing in here. In the case of fans and blowers also, where we said air is incompressible, there also approximately we can put this. Otherwise, we can always go in gases as Cp0 T2 minus T1 and work out from there. That's fine. But liquids, this is the important difference. And now let's see how do we show the process on property diagrams. Okay, this is TS, and one thing we need to know, okay, we need to here of course mention somewhere or check somewhere that this is valid in the given problem. Fortunately, what happens is when you compress it, it becomes more of a compressed substance. So as long as the inlet state is a compressed liquid, or in some cases a saturated liquid, the moment you compress it, it will become a compressed liquid. So if the inlet state is a compressed liquid, then we are safe that throughout it will be a compressed liquid and our assumptions are fine. That's something to check. Okay, now let's look at TS diagram. And second pump, we are pumping water at ambient conditions. And we know that ambient water is slightly compressed liquid, and when we compress it, the pressure goes up, and in the ideal case, it is adiabatic, and if it were reversible, it will go up over there, and this will be 1 to 2. I am exaggerating this, because as I showed you the TS diagram, the lines of 500 or 50 megapascal is pretty much very close to this, and so if I actually have to show this diagram, we can't even show it, simply because the effect of pressure on properties is so very, very small. But here we have done some exaggeration and showed it to clarify that inlet state is compressed liquid. This is isentropic compression in the ideal case. It has gone from there to there. The real compression will go to the same pressure. Isobars are like that. So the discharge valve pressure isobar goes somewhere there. But it is extremely close to this line, so it's very difficult to differentiate that. This is the isentropic case. This is the real case. If you are saying that we take saturated liquid and then we compress it, and that's what happens in a power plant thing, where we have condensed the water into a saturated liquid and then we start pumping it. So we can say that the initial state was here, and then we started pumping it and it went there. So it started one as a saturated liquid, went here, and in the ideal case it went slightly over there. Okay, so that's the pumping of a saturated liquid. In the practical world, this is a very tricky operation. So pumping saturated liquid, where do we encounter it? I've given the example of every power plant condenser or condensate pump. Also the main boiler feed pump. Then we are trying to compress a pump saturated liquid, and cryogenic engines. This was launching rockets very frequently these days, and they all have a cryogenic engine. When you have a tank containing saturated liquid oxygen, so there we can say that here's a tank, LO2, or there's another tank, liquid hydrogen. Both are saturated liquids at 1 bar pressure. And we take a pipe and we put it into a compressor that goes into the combustor. So here is the problem that happens with saturated liquid, that saturated liquid is a static case, but if I have a condition where it begins to move in a pipe, then because its velocity is increased, and what we have learned from thermodynamics is that here and here, if I apply the first law, here velocity is 0, here velocity is finite, so this was state 1, this is state 2, all the assumptions of steady state flow we take, then H1 is equal to H2 plus V2 square by 2. And even if V2 is very, very small, it tells you that H2 is less than H1 and pressure P2 is slightly less than P1. That means the moment you take this state and try to pump it, it will go there. Which means that some of the liquid became vapor and you ended up with a two-phase mixture, and that's the problem. Vapors, as you have seen, the specific volume is very large, suddenly the whole thing becomes crazy and the engineering becomes very, very difficult. And so we have to ensure that we give at least minimum some static head, so that this is saturated liquid, but as it goes down, the gravity head rho GH adds on to it, so the pressure here under no flow will be more than the pressure here, so it will be slightly subcooled liquid, slightly compressed liquid. Then as you pump it to the pipe up to the inlet of the pump, the pressure drop will take place, but at no place do we ensure that pressure is less than P sat at the given temperature. This is a very important consideration in designing all these type of devices. So even in a pump like this, where it is taking compressed liquid and you have an impeller that is rotating very fast, very close to the surface of the impeller, the velocity is very high, in which case locally the pressure at that point will be less than the saturation pressure at that point, and you could have a vapor bubble being formed. The moment this vapor bubble moves out into a zone where the pressure is more, it will compress suddenly and it gives out a shock wave, and that's why you will see that some pumps sometimes make a hammering sound, that there's something is being hit inside it. There's nothing hitting it, just that this device is happening, that vapor is being formed, and this is called the issue of cavitation. Even in the propellers of ships, especially naval ships, where the propeller is rotating in water, the surface, the velocity of the water adjacent to the surface of the propeller is high, its pressure will be less, and if the pressure becomes less than the saturation pressure at the ambient temperature of the water, it will become a vapor bubble, it will move out, collapse, leave a pressure wave, and that becomes a signature of that device, and somebody else can detect your ship. So it's a big challenge that you want to control cavitation, in that case for defense purposes, but in our cases here, because when these bubbles form and break, they send out pressure waves and they do mechanical damage very badly, and in no time at all, the machine can get destroyed. So we would like to take care of that. But this is why the thermodynamics tells you that an important thing like cavitation actually happens, and what we need to do is what engineering is all about. Okay, so pumps will always start in the either in the saturated liquid state and go up, or in the compressed liquid state and go up, but never in the wet region. Again, we handle only a single phase. Okay, so this is about pumps.